Okay, so this next little part is about simple harmonic motion. So just get my camera perfect. Seems to be wandering off. Okay, so this part is about knowing how the energy varies with a object in simple harmonic motion. Okay, so the first bit of information that we're told is a particle of mass m oscillates in a straight line with a simple harmonic motion of a constant amplitude. In other words, it's a straight line, so therefore it must be a spring. We don't know if this is irrelevant or not yet, although it's likely to not be, okay, because otherwise it would have told us it was a spring. But any object that oscillates in a straight line, okay, rather than a curve, obviously, is likely to be a spring. Okay, so that's a big pendulum, by the way. So it's such a particle of mass m, alright, and it has a total energy E. Now, just be aware of the varying types of energy that we have. So the total energy, okay, is split into two parts, kinetic and potential, okay, subscript E and subscript P and K, respective potential and kinetic, okay. Now, kinetic, obviously, you know, is a half of mv squared, and that's basic. Potential, okay, can be written in various ways, but because we've got a spring here, we can assume it is a half times k times delta L squared, or half times k times x squared, or a squared for maximum amplitude. So there's two ways that you can go about this, okay, for working out the answer. Okay, but obviously we need to get to the question first. So that's just aware of what they are. Also, when one is a maximum, obviously the other will be zero, because its total energy does not change. These two will always add up to the total kinetic energy, irrespective of what part of the oscillation this object mass m is. Okay, so the kinetic energy will be a maximum at the point of no displacement. That's what x represents, displacement, okay, from the equilibrium position. And obviously vice versa, as I said. So your energy curves will look something like this. If you remember that little box, I don't know if you were showing it, where your two upside down curves, and they will always both add up to this total bit of ET. Okay, I don't know if you remember that, it's kind of a crappy drawing, but this corresponds with that, okay? So what is this question actually asking? So let's just put you in the mindset of it again. So we've got another particle of mass 2m, in other words, double the mass, okay? And it's oscillating with simple harmonic motion with the same amplitude but double the frequency. Okay, so how are we going to go about this? Sorry, what is the total energy of another mass particle mass 2m with the same amplitude but double the frequency? So we've got to find out what this is. Now, this is one of those questions where it's a comparison question, and what I mean by that, so I'm just getting another pen, this one's useless. What I mean by that is we know what the total energy is for a particle of mass m, which is shown at the top left, which is E, okay? We need to know what that is, so we've got an equation there for the total energy, ET, which is equal to EK plus EP, and we need to work out what that is for this particle, and then how many times bigger or smaller this new one is for this other particle, taking into consideration the bit of information we've been told. But I want to go from the idea that when either the total energy is the maximum, when the kinetic energy is the maximum, the potential energy will be zero. Now, which is going to be easier? Bear in mind, we've got to take into account the fact that it's the same amplitude but double the frequency. So, is the kinetic energy going to give us that? Or, so in other words, are we going to be able to alter the equation? Okay, because obviously the left-hand side we don't know, so we need to make the right-hand side similar to before so we can compare it. You know, that'll become obvious when we actually get around to doing it, okay? So I really don't know where this pen is. Let's pause it again. No, yeah, I can't. So, which is going to be easier? Okay, well, it's not going to be the potential energy, that's for certain, because the only thing we can change about that is the displacement, and that is relevant to what we're talking about. So it must be some way of altering the kinetic energy. Okay, now it doesn't look at it straight off the bat because it's a half of mv squared. And with a v, okay, because we're not talking about circular motion, so we don't do the 2 pi r over t. So we look in the equation sheet for the velocity equation, okay? And the velocity equation in the simple harmonic motion book is 2 pi over t, or 2 pi f a, okay? I'm going to use the 2 pi f times the displacement times x. Now, the reason I'm using x to be a in this case is because a simplifies the amplitude. The maximum amplitude is therefore the maximum displacement, so we can write amplitude for the displacement. Okay, it's maximum. So this is the maximum velocity. So therefore, applying this to this case will give us the maximum velocity. Okay, or the maximum energy. Now, the reason I'm not putting the double amplitude or whatever is because we need to see what it's like with the single particle of mass m. Okay, so the total energy Et is equal to E, okay, when we're talking about this particle of mass m. Okay, so half of mv squared is equal to half times m times v all squared. So 2 pi times f times a all squared. Okay, and obviously you could therefore simplify this and work this out. Okay, so therefore it's a half times m, so that bit doesn't change, and then we're going to square 2 pi f a. Okay, so that's going to give us we can leave it like that actually, yeah, you can leave it like that, it's going to be easier. Now what we need to do is apply what is the total energy, so that's what E is equal to. What's this new total energy equal to when we double the mass? Okay, so what's happening here, just note it down for you. So we're doubling the mass and same amplitude, so A remains the same, but we're also doubling the frequency. So these are the changes, or not changes, that are happening here. So again, we're going to compare it to something like this. Okay, so we're going to use it when the total kinetic energy, when the total energy is equal to the kinetic energy, because that's when it's a maximum. Okay, so put it in here. So E is equal to half times, now it's not just m, because we're doubling the mass, it's half times 2m. Granted that would just be total m, but we need to carry on with this as normal. And then it's 2 pi times f, but our new f is 2, what it was before. So 2 pi times 2f, and the amplitude remains the same, so times a all squared. So what is the difference? So what we need to do is simplify them down and compare them. Okay, so the top one therefore obviously will be E is equal to m over 2 times all of that squared. So I'm doing it in very slow stages, so it's m times 2 pi f. Now that won't just be 2 pi 2f, you could write that as 4 pi f, because we're taking into account the 2f there, times a, and we're squaring all of that. Okay, so what does that come to? Okay, so sorry. Now because we're squaring this, we need to square each bit inside of it. Okay, so it's m over 2, and then times, well this comes to, if you square the 2, you get 4 pi f a. Okay, and then if you square this, you get m times 16 pi f a. Obviously that's squared and that's squared. Okay, now we're just comparing them here. Okay, so if we half of that, then we get 2 mass pi f squared a squared. Okay, so that's the total energy for the particle of mass m. Work it out here. So it's 16 m pi f squared a squared. So we're comparing these two. Okay, so this here at the bottom is the total energy for the new particle of 2m, and this is the total energy for the particle of mass m. Okay, so what's the scale factor to get from one to the other? Okay, well they've both got single m here. Well, one's got 2m, one's got 16m. This has got pi, that's f squared, that's f squared, that's a squared, that's a squared. So the only difference here is between the 2 and the 16. So how many times bigger or small? bigger is the mass of 2m. In other words, the total energy difference. So you could divide 16 by 2, alright? Or just divide that by that, they will all cancel, okay, same way. So therefore, the mass of the new particle is 8 times the mass of the old particle, so therefore it's a scale factor of 8, and we're asked what is the total energy of the old particle? Well, of the new particle, sorry. Well, the total energy of the old particle is E, okay, and this one's 8 times bigger, so therefore it's 8E, which if you look on your list of answers is option D, so therefore 8 is also D. Okay, this next bit is also on simple harmonic motion. Sorry, I just wanted to go through that bit and just make sure you were fully aware of what I was waffling on about. Okay, so this new, get it up on this thing. Question 9 says, when a mass suspended on a spring is displaced, the system oscillates with a simple harmonic motion. Which of the following statements regarding the energy in the system is incorrect? Okay, so it is going off from this bit again. It's linking in, using the idea of the fact that the energy is a maximum. Okay, it is always a constant of the total energy, in this case E. All right, but this is the question before, just highlighting the obvious. And when the kinetic energy is a maximum, the potential energy is 0, and when the potential energy is maximum, the kinetic energy is 0. And the kinetic energy is greatest at the point 0 displacement, and the potential energy is the greatest at the maximum displacement. Okay, so using that bits of information, okay, with the velocity being the greatest at the centre, the equilibrium position, the acceleration being the greatest at the maximum position, in other words, the amplitude, okay, using them ideas should be enough to help us with these separate points, okay? So, as I said, sometimes in these questions, as we had before, there'll be two answers that say opposite things and one of them must be right and the other two therefore must be wrong, okay? So, let's go through the possible answers, see what they say. And if we have any that are like that, okay? So, the first one says, the potential energy has a minimum value when the spring is fully compressed or fully extended. Well, that argues straight away with the point we made before about saying the potential energy is a maximum when the displacement is maximum. In other words, the potential energy has a maximum value, not a minimum value as point A says, when it is fully compressed or extended. Okay, so therefore A must be incorrect. But let's just go through your options. The kinetic energy is a minimum value at the equilibrium position. Sorry, maximum value at the equilibrium position, which is correct, which is what we said. The sum of the kinetic and potential energies at any time is constant. Well, that's also true because the kinetic energy and the potential energy total the total energy, which is what option C says. Option D says the potential energy has a minimum value when the mass is at rest. Well, the mass is at rest when it's at a maximum or a minimum. So basically, A and D say opposite things. So therefore, A or D must be incorrect or correct, whichever way you look at it. So therefore, your answer is either going to be A or D. So therefore, it is A. Sorry, just someone trying to sell PPI. I'll just put further. Okay, so that's question 9. Question 10 is about springs. Okay, now this recalls on your knowledge about springs in a series and springs in parallel. Okay, so when you have springs in series, you add the you work out the effective spring constant. Okay, and I always anticipate it being the opposite of a of working out the effective resistors in parallel or series. Okay, back from unit 1. Okay, so just find a rubber somewhere. Use this. Okay, so whenever you have springs in series, if the spring is the same, which it will be if it's asking you about the effective spring constant, you just have to remember it's half of what it was before. Okay, if you have two in series. Okay, so we've got one spring on its own. Sorry, we've got one spring on its own here. The mass M. Okay, and another spring. Sorry, my drawings are terrible. Okay. So both got a spring constant of K, and this other one has a spring constant of K. Okay, so we've got two different setups there, and the question says, when a mass M is attached to a spring in figure 1, okay, which is the single spring on the left, it oscillates with a time period t. So just label that t. Now, because initially it's talked about the time period, you should be aware, I mean it's in the formula book anyway, but the time period for the time of a spring is 2 pi times the square root of m over k. Okay? So m being the mass and k being the spring constant. And predictably it's going to ask us the time period of this other one in comparison. So an identical spring is connected in series with a mass 10 attached as followed. So basically it's asking, this is the time period of this one, in respect, what is the time period? One. Excuse me, sorry. Great cough. Hopefully you can't yet get virus television, but that'll be coming soon. Okay. Oh dear. Yeah, so basically it's about comparing one time to the other. Okay, so we're not given any numbers, nothing to work out, there's no mass values given, so there's nothing we can do in terms of that. So what do we do? Okay, so you can either work it out logically, and just remember when you, because obviously this is going to be now, that's the only thing that's going to change, okay? I think it even tells you. So K is going to half, okay? So because in a series, okay, for springs, the effective spring constant is adding the spring constants together, K1 plus K2, okay, excuse me, is the effective spring constant. So it's the other way round for the constant in a series. Okay, so it's 1 over K1 plus 1 over K2 is equal to 1 over the effective spring constant. Okay, so that's for springs in a in series. Sorry, that's springs in parallel, sorry. This is what this is. Sorry, oh my god, I said series first, yeah. This was springs in series and the other one is for parallel. Okay, and the way, now if you don't get what I'm saying about the fact that they add up in the opposite way to resistors, it's because you add it in the same way to resistors but the other way around. Okay, so if K was a symbol for the resistance, okay, this would be a series one, this would be a parallel one. Okay, but because we're talking about springs, it's the other way round. Okay, so this is for parallel and that's for series springs. Okay, we count this as a series because they're directly connected. Okay, parallel is where you have, you know, like that, and you have the bar, and there's a point down, you have a spring here and a spring there. Okay, that would be parallel. Okay, but because we're talking about series, you work it out there. Now you could just work out what this is. Okay, but essentially, as I said, you halve K. So therefore, when you put it into the equation, you get it's root 2 times bigger. Okay, just trying to skip through this one. So you work out what this is. Okay, so K is the same, so 1 over K. So it's 1 over 2K is equal to 1 over K. Okay, so in other words, flipping it, your K is halved. Is that right? Yeah. Yeah, that's right. Is it? Yeah. Sorry. Yeah. K is halved, so therefore this is at 2m over K. Okay, for this one here now. So therefore you're comparing T is equal to 2 pi times the square root of 2m over K, and you're comparing that to this equation here for the single spring, okay, which you know is T. So in comparison, what is, if you're to put that is equal to T, what is this equal to? Okay, so you need to make this equation look like this. In other words, get this 2 out of here, okay, And you could do that a very, very long way round by timesing this out, multiplying it round and see what the difference is, okay? But essentially, what it comes to is it's root 2 times larger, okay? Because obviously this is going to have a longer time period, so it's root 2 times t. Okay, because whenever you do a square root of something like this, you're basically taking out this over here, and the power stays with it, so it's root 2, it's a square root of 2. Just like when you take anything out, because instead of writing this as a square root, you could write it as to the power of a half. And whenever you take something out of, say, binomial expansion in C4, when you're converting it and you're taking something out of the bracket, okay, you keep the power with it, okay, because we're taking this 2 out of the bracket, we keep the power with the 2 as well, okay, so therefore it's 2 to the half when we take it out of here, so therefore it's 2 to the half, the square root of 2 times all of this, which is times t, okay, so hopefully that makes some kind of sense to you. So therefore root 2 times bigger, so therefore the answer for 10 is C. Sorry, I didn't put what didn't write the answer down for 9. Sorry, that was 9 was A. Sorry about that. Should have said that. Okay, so that's question 10. Okay, so that's the end of the simple harmonic motion stuff. I'm just going to pause the video and we'll continue from question 11 onwards.